Imagine, for a moment, that it is a quiet evening in the year 1959, and you are standing at the bottom of a stairwell inside a physics building at Harvard, a place called the Jefferson Physical Laboratory. It is the kind of stairwell you have stood in 100 times without thinking about it. Grey steps. A cool draft moving down from somewhere above. The faint smell of old stone and older dust, and rising up through the middle of it, running from the floor near your feet all the way to the ceiling far overhead, there is a tall, narrow tower of pipe and metal, about 22.5 meters high, 74 feet, more or less, tall enough that if you tipped your head all the way back and looked straight up, the top of it would seem to shrink into shadow. There are two men here tonight. One of them is a physicist named Robert Pound. The other is his graduate student, a younger man called Glenn Rebke. And what they are about to do, very slowly, very carefully, in this ordinary stairwell, is something that people had spent nearly 50 years assuming could only ever be seen across the vast dark distances between stars. They are going to weigh a beam of light. Not with a scale, exactly. Not with anything you could hold. But they are going to catch light in the act of losing a tiny sliver of itself as it climbs. And they are going to prove that gravity, the same gravity holding you gently against your bed right now, reaches up and quietly steals a little energy from light simply for daring to climb away from the Earth. That is where we are going tonight. Up that tower, one careful step at a time. But before we climb it, let me welcome you properly. Welcome to the curious Voyager. It really is lovely to have you here. Wherever you are right now, whatever hour it happens to be, in your particular corner of the world, I hope you are somewhere soft. Maybe you are tucked under a blanket with the lights already low. Maybe there is a lamp still glowing in the corner that you have not quite talked yourself into turning off. Maybe you are on a train or a couch or lying flat on your back staring up at a ceiling you cannot even see in the dark. It does not matter where. You are welcome here, and I am glad you came. And I am a little curious, honestly, where in the world are you listening from tonight? What time is it in your part of the night? You do not have to answer, of course. But if you feel like it, leave a little note down below and tell me. I always love reading them, imagining all these quiet rooms scattered across the planet, all of us drifting towards sleep together while we think about something strange and beautiful. And if you enjoy these slow journeys and want more of them, a gentle like and a subscribe genuinely helps this sleepy little channel keep going. Small creators like me really do rely on that kind of quiet support, and to those of you already subscribed, wandering back here night after night, thank you. Truly, you are the reason this exists. Now, here is my promise to you, and I mean it. We are going to take this slowly. There is no rush tonight. None at all. I am going to walk you through one of the strangest and most delicate experiments in the history of physics, but I am going to do it gently. One small idea at a time, and I am going to translate every difficult word the moment it appears, so you never once have to feel lost or feel foolish. You do not need to understand every detail. You do not need to hold any of it in your head. In fact, if you drift off somewhere in the middle of the story, before we ever reach the top of that stairwell, that is completely fine. That is allowed. That is, if anything, the whole idea. The story will still be here when you wake, and gravity will still be gently pulling on the light, and nothing will be lost. I will try my very best not to make this so interesting that it keeps you awake. But if it does, well, at least you will have learned something lovely on your way to sleep. A fair trade. So settle in. Let your shoulders drop a little. Let the weight of the day sink into whatever is holding you. And let us begin, softly, at the very beginning, which means we have to go back a little further than 1959. We have to go back to a man with wild hair and a quiet, restless mind, sitting at a desk in the early years of the 20th century, thinking about something so simple that almost nobody had ever thought it worth thinking about at all. The man, of course, is Albert Einstein. And the simple thought that changed everything was this. He imagined what it would feel like to be inside a falling box. A lift, say, with its cable cut, dropping freely through the air. And he realized something curious. If you were inside that falling box, floating, everything drifting weightless around you, you would have no way of knowing whether you were falling in gravity or simply floating far out in empty space, where there was no gravity at all. The two situations would feel exactly the same. There would be no experiment you could do inside that sealed box to tell them apart. And then he turned it around. Imagine instead you are inside a box being pushed upward, accelerating, out in empty space, far from any planet. You would feel pressed to the floor. You would feel heavy. And Einstein realized that this feeling, the feeling of being pushed by acceleration, would be utterly indistinguishable from the feeling of standing still inside gravity. Being accelerated and being held by gravity are in a deep sense the same thing. He called this idea the equivalence principle, and he first began circling around it as early as 1907, developing it over the next few years toward around 1911, well before he had finished the full, magnificent machinery of his general theory of relativity, which would not arrive in its complete form until 1915. And here is the thing that makes this so lovely. You do not need the whole enormous theory of general relativity to see what comes next. You only need that one simple idea. Gravity and acceleration are the same. Because once Einstein believed that, a very strange consequence followed almost immediately. Like a shadow, the idea could not help but cast. And the consequence was about light. Let me walk you through it slowly, because this is the seed of the whole night. Picture, again, that box being accelerated upward through empty space. Now imagine someone shines a beam of light across it, from the floor toward the ceiling. The light leaves the floor, but because the box is accelerating, by the time the light reaches the ceiling is moving away from it, just a little faster than the floor was when the light set off. And when a source of light and a receiver of light are moving apart, even by the tiniest amount, something happens to the light. Its waves get stretched, they arrive a little more spread out than they left. And light with more stretched out waves is light that has shifted ever so slightly toward the red end of the colours. This stretching is called a redshift. Red, because red light has the longest, most stretched out waves of all the colours we can see. So the light climbing from floor to ceiling in that accelerating box arrives very slightly redder, very slightly drained than it began. Now here comes the beautiful leap. Einstein said, if acceleration does this to light, and if gravity is exactly the same as acceleration, then gravity must do it too. Light climbing upward through gravity, light travelling away from the Earth, away from the source of the pull, must lose a little energy on the way up and arrive very slightly redder than it started. Not because anything is moving, just because it is climbing. Just because it is fighting its way up and out of the Earth's gravity. And the climb costs it something. This is what physicists came to call gravitational redshift. Sometimes it is called the Einstein shift, after the man who first predicted it. And I want to be careful here, because there are other kinds of redshift in the universe, and I do not want you to confuse them as you fall asleep. There is a redshift from things rushing away from us, and there is a redshift from the whole universe stretching over billions of years. Those are different creatures entirely, and we are not talking about them tonight. Tonight we are talking only about this one particular, gentle, local thing. Light losing a whisper of energy simply for climbing upward against gravity. That is our whole story. Keep your eyes softly on that and let the rest drift past. Now there is a second way to picture this, and I love it because it makes the whole thing feel almost solid, almost like something you could hold in your hand. It is the reason this video is called what it is. It is the idea of weighing a falling photon. A photon is just the smallest possible piece of light. A single grain of it. Light comes in these tiny packets, these little grains, and each grain is a photon. Now, a photon has no weight in the ordinary sense. It has no mass the way a pebble or a feather has mass. But Einstein had shown in that famous little equation everyone half remembers that energy and mass are two faces of the same thing. Energy behaves as though it has a kind of mass. And a photon carries energy. So a photon, as it climbs, behaves as though it carries a tiny sliver of mass, as though it weighs, just barely, something, and if it weighs something, then climbing costs it. Think of yourself climbing a flight of stairs. You reach the top slightly more tired than you were at the bottom. You have spent some energy lifting your own weight against the pull of the earth. Physicists have a tidy little way of describing that cost. They call it the work you do against gravity, and for something of a certain mass climbing a certain height, that cost is the mass times the strength of gravity times the height you climbed. Mass times gravity times height. Now do exactly the same thing to a photon. The photon has its little sliver of effective mass. It climbs a height. And it pays the same toll. It arrives at the top with a little less energy than it had at the bottom, drained by precisely the amount it spent climbing. And for light, less energy does not mean it slows down, because light cannot slow down. Instead, less energy means its waves stretch, means it reddens. The photon climbs the stairs, arrives at the top a little more tired, a little redder, having paid its fare to gravity along the way. That is the sense in which you can weigh a falling photon. You watch what climbing costs it, and from that cost you read its weight. It is a strangely tender image when you sit with it. Light, the fastest, lightest, most untouchable thing in the universe, still has to trudge uphill against gravity like the rest of us, and still arrives at the top, a little worn down by the climb. Nothing gets to skip the fare, not even light. So Einstein had his prediction. Light climbing away from the Earth should lose energy and redden by a definite, calculable amount, and physicists could even write down exactly how much. They had a little relation for it, and I will give it to you gently, because the numbers themselves are part of the wonder tonight, not because you need to remember a single one of them. The fractional shift, meaning how big the change is compared to the light you started with, is given by the strength of gravity times the height climbed, divided by the speed of light multiplied by itself. Gravity times height over the speed of light squared. That is the whole recipe. And you can already feel, just from the shape of it, that this is going to be a very small number, because the speed of light is an enormous number, and here it is being multiplied by itself and then dividing everything else. Whenever you divide by something gigantic twice over, what you are left with is something very, very tiny. and tiny it is. Let us actually put the stairwell into the recipe. The strength of gravity at the Earth's surface is a number around 9.8 in the units physicists use. The height of that tower in the Harvard stairwell was about 22.5 meters. Put those in, divide by the speed of light multiplied by itself, and out comes the number that Pound and Rebke were hunting. And the number is this. About 2.5, followed by a decimal point, pushed 15 places to the left. 2.5 parts in 1,000 trillion. I want to let that number just sit in the air for a moment, because I do not think our minds are really built to feel a number that small, and it is worth slowing down to try. 1,000 trillion. Imagine you had 1,000 trillion identical grains of sand, all poured out into one impossibly vast, smooth field, every grain the same, and somewhere in that field you changed just 2.5 of them. 2 grains and a little of a third. That is the size of the change Pound and Rebke were trying to detect in the colour of light. Not 2.5 grains in a bucket. Not 2.5 grains in a truckload, 2.5 grains in 1,000 trillion. The light going up their tower would arrive redder by that much, and only that much, and their whole task was to notice it. Or think of it another way, because I want this smallness to really land softly before you sleep. Imagine a clock so perfect that it kept time flawlessly. And imagine you wanted it to lose or gain time by this same fraction, 2.5 parts in 1,000 trillion. You would have to wait millions of years for the error to add up to a single second. That is how steady, how untouched, how perfectly unchanged the light seems, to any ordinary way of looking at it. The shift is there. Einstein's equation insists it is there. But it is buried so many layers beneath what any normal instrument could feel that for decade after decade after decade, it may as well not have existed at all. It was a real number sitting just below the floor of everything anyone could measure. And that really is the ache at the centre of this whole story, and the reason it is beautiful. Einstein had made a clear, specific, unmistakable prediction. Light loses energy climbing out of gravity by this exact tiny amount. But the amount was so absurdly small that here on Earth, over any height a human being could actually build or climb or arrange, it seemed hopelessly, permanently beyond reach. You could write the number down, you simply could not catch it in the act. So for a long time, the only place anyone thought they might ever see this effect was out in the sky, where gravity comes in the truly enormous helpings that stars and dense collapsed suns can provide, and where light might climb out of a gravity so fierce that the reddening finally grows big enough to notice. We will come to those attempts, the shaky starlight evidence, the flawed and famous measurement of a faint companion star, in a little while. And we will come to the astonishing trick, a nucleus frozen so perfectly still inside a crystal that it can throw out a grain of light without so much as flinching, that finally dragged this cosmic prediction down out of the sky and pinned it to a bench in a basement stairwell. But not yet. Right now, I only want you to hold softly this one shape of the problem, because everything else tonight grows out of it. On one side, a prediction as clean and confident as any Einstein ever made. Light climbing away from the Earth must redden, must lose energy, must pay its fare to gravity. On the other side, a number so vanishingly small, 2.5 parts in 1,000 trillion over the whole height of a building, that it seemed to belong forever to the realm of things that are true but can never be touched. 2 men in a stairwell in 1959 decided they were going to touch it anyway. Picture them again down there at the bottom of the tower. The building is quiet. Most of the physicists have gone home. There is the low electrical hum of equipment that has been left running, because an experiment this delicate cannot simply be switched on and off like a lamp. It has to be coaxed, warmed, settled, watched over for hours and hours, while it slowly gathers the faintest possible whisper of a signal out of the noise. At the bottom of the tower there is a small source, a speck of radioactive material, throwing out grains of light of a very particular kind, a very high, very pure kind of light that we will get to know well tonight. At the top of the tower, 22.5 meters up, near the ceiling, there is a detector, waiting, counting, patiently registering each grain of light that survives the climb. And the entire question of the experiment, the whole enormous delicate point of it, comes down to this. Do the grains of light that arrive at the top come in very slightly drained, very slightly redder, by exactly the 2.5 parts in 1,000 trillion that Einstein's equivalence principle demands? Because if they do, then something wonderful is true. Then gravity bending the color of light is not some remote astronomical rumor, some smudge on a photograph of a distant star that might just be an error. Then it is a plain, solid, measurable fact of the world, something that happens between the floor and the ceiling of an ordinary building, something that would be happening in the room you are lying in right now, to the light of the lamp you have not turned off. If only you had eyes fine enough to see it. That is the prize. And the whole rest of our journey tonight is the story of how on earth you build eyes fine enough to see a thing like that. Because you should feel, right now, that it ought to be impossible. Truly impossible. Think about what they are asking of themselves. They need a source of light so absolutely perfectly pure in its color that they can tell when it has shifted by 2.5 parts in 1,000 trillion. Everything in ordinary experience is far, far too blurry for that. The light from a candle, the light from the sun, the light from any glowing thing you have ever seen is a smear, a blend, a wide, soft band of many colors all mixed together and jittering about. Asking such light to reveal a shift of parts in 1,000 trillion is like asking someone to notice that a single wave on the whole restless surface of the ocean has risen by the width of a hair. The information is drowned before you even begin. So the deepest part of this story, the part the ordinary tellings skip right past, is not really about the tower at all. It is about sharpness. It is about how you find or make a beam of light whose color is defined so exquisitely, so finely, so much more precisely than almost anything else in all of physics, that a shift of a few parts in 1,000 trillion is no longer lost in a blur, but stands out like a single clear note held in a silent room. Without that sharpness, the tower is useless. With it, the tower becomes a way of catching light in the act of paying its fare. And the source of that sharpness, when it finally came, arrived from a completely unexpected direction. Not from anyone hunting for Einstein's redshift at all. It came from a young graduate student in Germany, working on something that seemed to have nothing whatsoever to do with gravity, who noticed that when you freeze an atom's tiny core into the rigid heart of a crystal and cool it down, something almost magical happens to the grains of light it throws out. They come out perfect, unblurred, sharp as anything in nature. And that unlooked-for gift of sharpness would turn out to be precisely the tool that 2 men in a Harvard stairwell needed to weigh a falling photon. But to understand why that gift was so miraculous, we first have to understand why light from an ordinary atom is so hopelessly blurry in the first place, and why an atom's core, left to itself, seems almost designed to ruin any hope of the sharpness we need. We have to understand the recoil. We have to understand the little kick that a tiny thing gives when it throws out a grain of light, and how that little kick, multiplied and jostled and smeared across countless atoms, spoils everything. So let us drift gently toward that. Let us leave Pound and Rebke standing at the foot of their tower for a while, the equipment humming, the detector waiting patiently up near the ceiling, and let us go back a little and understand the enemy they faced. Because before anyone could measure this shift, they had to defeat a problem that had defeated everyone before them. And the shape of that problem is where our story turns next. Rest here a moment first, though. Let me gather the thread for you, softly, the way you might smooth a blanket before settling deeper under it. So that if you are still with me, you can carry the whole shape of it into whatever comes next. And if you are drifting, you can let it go, knowing it will keep. We have a prediction. Einstein, from one simple thought about a falling box, from the idea he called the equivalence principle, worked out around 1907 to 1911, saw that gravity and acceleration are the same thing, and that therefore light climbing away from the Earth must lose a little energy and shift toward the red. We have a picture for it. A photon, a single grain of light, carries energy, and energy behaves like a little sliver of mass, so the grain of light has to pay a toll to climb, mass times gravity times height, arriving at the top a touch drained, a touch redder, the fare taken by gravity along the way. And we have a number. Gravity times height over the speed of light multiplied by itself. For a tower 2.5 meters tall, that number is 2.5 parts in 1,000 trillion. A shift so small it seemed forever beyond touching. A real truth hidden below the floor of everything anyone could measure. And we have two people, Robert Pound and his student Glenn Rebke, standing at the bottom of a stairwell in the Jefferson Physical Laboratory at Harvard. In the year 1959, who had somehow decided that beyond touching was not the same as beyond reach. Who believed they had, at last, a source of light sharp enough, pure enough, fine enough in its colour to catch that impossible sliver of a shift as gamma rays climbed their tower and arrived, ever so slightly, drained, where that impossibly sharp light came from, and the frozen, flinchless nucleus at the heart of it, and the young man in Heidelberg who stumbled onto it while looking for something else entirely, is where we are headed. But there is no hurry at all. The tower is not going anywhere. The light is still climbing, patiently, the way it has climbed, for as long as there has been gravity to climb against. And you have nothing to do tonight but breathe, and rest, and let the strangeness of it settle over you like a second, quieter blanket. So let your eyes stay closed if they have already found their way there. Let the number 2.5 parts in 1,000 trillion drift off somewhere out of reach, where you do not need to hold it. And keep only this, if you keep anything at all. Somewhere, right now, in a stairwell that has long since gone quiet, light is climbing upward against gravity, and paying, in the smallest coin there is, for the privilege of the climb. And two patient people found a way to watch it pay. We will follow them up the tower, slowly, in just a little while. But before we climb, we should understand why nobody had climbed before, because the prediction had been sitting there for a long time. Decades. Einstein had worked it out as early as 1907, 8 years, before he even had the full field equations of general relativity in hand. It fell out of something simpler. Something he called the equivalence principle, which is the idea that a person standing still in a gravitational field and a person being accelerated through empty space cannot tell the difference. They feel exactly the same thing. Their feet pressed to the floor with exactly the same insistence. And if that is true, Einstein reasoned, then light must behave in both situations identically. And light bending, light shifting, light losing a little energy when it climbs, all of that follows. Quietly, inevitably, like a consequence you were always going to have to accept. So the prediction was not new when Robert Pound and Glenn Rebka set up their apparatus at Harvard. It was old. It had been written down and published and discussed and folded into textbooks. And in the decades between Einstein writing it down and those two men standing in that stairwell, people had tried to find it, had looked for it, had hoped, perhaps, that the universe would show them the evidence they needed without requiring them to do anything quite so difficult as build a machine precise enough to see it. They looked first at the stars, which is a reasonable place to look. Starlight, light that has climbed not a flight of stairs, but an entire gravity well, an entire compressed and massive object, before it travels across the dark to reach us. If there were anywhere you would expect to see a gravitational redshift, you might think it would be in the light from a star dense enough to hold it strongly, dense enough to make the climb genuinely steep. And so there was a moment in 1925 that looked like exactly that. An astronomer named Walter Sidney Adams measured the spectrum of Sirius B. Now, Sirius B is worth a moment of your attention wherever you are settled right now, because it is one of the stranger objects in the night sky that most people never think about. Sirius itself, Sirius A, the bright one, the dog star, the brightest star visible from Earth, that one everyone knows, or at least everyone knows its light. But Sirius A has a companion, a white dwarf, a star that has used up its fuel and collapsed down to something roughly the size of the Earth, packed with the mass of the Sun, small and dense and intensely gravitational. And if you were a photon of light produced in its core and trying to leave, you would have a significant amount of gravitational well to climb on your way out. The redshift from that kind of climb, off a white dwarf, rather than off something as diffuse and modest as our own sun, should be large enough, in principle, to be visible in a spectrum, detectable with the instruments of the time. Adams looked, and he measured, and the spectrum of Sirius B did appear to be redshifted, by roughly the amount you might expect from general relativity's prediction, given the mass and size of the star. It looked like confirmation. For a time, it was cited as confirmation, and in one sense the measurement was pointing in the right direction, the shift was real, and it did have a gravitational contribution. But it was also a mess. Because Sirius B is not an easy object to look at cleanly. It sits right next to Sirius A, which is blazing, brilliant, overwhelming. Scattered light from Sirius A bleeds across the spectrum of Sirius B like glare from a lamp falling across a faint watercolor painting. The two become entangled in the instrument, and what you think you are measuring from the faint companion is partly, unavoidably, contaminated by light from its much brighter neighbor. The systematic errors in Adams's measurement were significant. Large enough, later analysis would show that the agreement with Einstein's prediction was more a matter of luck than of precision. The contamination had smeared the result into something that looked right, but could not, honestly, be trusted as proof. Not the kind of proof that should close a case, not the kind of evidence that should let a prediction rest easy. It was a cautionary story, actually, a reminder that the universe is not always generous about separating the signal you want from the noise you do not, and that a result pointing in the right direction is not the same as a result pinned down cleanly. The Sun's own redshift was similarly muddy. There was a shift in solar spectral lines, yes, but the surface of the Sun is not a still, quiet thing. It is a churning, convecting, turbulent mass of hot gas, and all of that motion produces Doppler shifts of its own, lines pushed around by gas moving toward us or away from us, lines broadened and smeared by thermal motion. Lines shifted by pressure in ways that can mimic or mask the gravitational effect. Disentangling the gravitational redshift from everything else happening in solar spectra turned out to be an exercise in ambiguity. Physicists tried. They got results that were broadly consistent with Einstein's prediction. But consistent with is a long way from confirmed by. You can be consistent with something and still be off by 30% in an inconvenient direction, with error bars that cover both outcomes. For half a century, then, the gravitational redshift remained in a peculiar position. Theoretically, it was solid. Nobody seriously doubted it. But experimentally, the evidence was frustratingly soft, astronomical, contingent, dependent on knowing the mass and size and composition of a distant star well enough to predict what the shift should be, and then comparing to a spectrum tangled up in noise. The prediction sat there, quiet and confident, and the evidence sat beside it, fidgeting, never quite convincing enough to put the matter to rest. What was needed, everyone could see in principle, was a controlled measurement. A laboratory test, something where you knew exactly the height, exactly the gravitational field, exactly the source, and could watch the shift happen cleanly, without stellar winds or convective motions or the glare of a companion star. Something you could build, something you could point. But to build that, you needed something that no one in 1925 had the faintest idea how to get their hands on. You needed light, or something behaving like light, with an almost impossibly sharp, precise color. Let us think about what color means here and why sharpness matters so much. Because this is the heart of the whole problem, and it deserves a few minutes of careful attention before we move on. When we talk about the color of light, we are really talking about its frequency, the rate at which the electromagnetic wave oscillates. Blue light oscillates faster than red. Gamma rays oscillate very fast indeed, far faster than visible light, far faster than X-rays even, occupying a range of the electromagnetic spectrum well above anything your eyes could respond to. And when we talk about a spectral line, the specific frequency at which a particular atom or nucleus emits or absorbs light, we are talking about a particular frequency in that spectrum, a particular note in a very high register. Now, in an ideal world, every atom of a given kind, every nucleus of a given type would emit its characteristic light at exactly one frequency. Perfectly defined, infinitely sharp, a single point on the spectrum, a pure tone with no breadth to it at all. But we do not live in an ideal world. We live in a warm one. And in a warm world, atoms and nuclei are moving. They are jittering with thermal energy, shaking with the heat of their surroundings, drifting and tumbling in the gas or liquid they inhabit. And when a moving source emits light, the frequency of that light is shifted. Slightly higher if the source is moving toward you, slightly lower if it is moving away. This is the Doppler effect. You know it from sound, a siren rising in pitch as an ambulance approaches and falling as it passes. Light does the same thing. In a sample of many atoms at any temperature above absolute zero, the atoms are moving in every direction, fast and slow, toward you and away from you, a whole distribution of velocities. So the light they emit comes out not at a single sharp frequency, but spread across a range of frequencies, each one slightly Doppler shifted by the individual atom's motion. The spectral line is not a knife edge, it is a smear, a Doppler broadened blur. For most purposes of spectroscopy, this is not a fatal problem. The lines are broad, but you can still identify them, measure them, use them. Chemists and astronomers have built entire sciences on the analysis of these smeared lines. But for catching a shift of 2.5 parts in 1,000 trillion, a shift that moves a line by 2.5 parts in 10 to the 15th power, a smeared spectral line is absolutely useless. The broadening from thermal motion is millions of times larger than the gravitational shift you are trying to detect. It is like trying to measure a change in the width of a human hair against the background noise of a storm. The signal drowns. It was not that people were not clever enough or not trying hard enough. The tools simply did not have, built into them, anything like the precision required. You would need a spectral line so sharp, so precisely defined, that its natural width was far smaller than the gravitational shift, so that the tiny displacement of the line would be visible rather than swallowed. And spectral lines just were not that sharp. Not in atoms, not in any source physicists could get their hands on. Except, it turned out, in something unexpected. Something not an atom at all, but a nucleus, and even then, only under the right circumstances. Only when something slightly miraculous was arranged, something that nobody had thought to look for, and that a young graduate student in Heidelberg stumbled upon almost by accident while working on a quite different problem. But before we meet him, we need to understand one more thing that was in the way. Something even more fundamental than Doppler broadening. Something that would have ruined everything, even if you somehow managed to cool your atoms to stillness and eliminate thermal motion entirely. Something built into the physics of emission itself. When a nucleus emits a gamma ray, something else happens at the same moment. The nucleus kicks back. It recoils. Think of it this way. A gamma ray carries momentum. It has to. It is a particle of light, a photon, and photons carry momentum as surely as they carry energy. When the nucleus spits out that gamma ray, it is like firing a tiny cannon. The cannonball flies one way, and the cannon kicks back the other. Conservation of momentum demands it. There is no getting around it. The nucleus recoils. And that recoil costs energy. Some of the energy that was going to go into the gamma ray goes instead into the kinetic energy of the recoiling nucleus. So the gamma ray that emerges from a free, unattached nucleus carries slightly less energy than the transition energy in the nucleus itself, slightly less than it should. By how much? For the particular gamma ray we are interested in, the one from iron 57, with an energy of 14.4 kilo-electron-volts, which is the transition that would eventually become the workhorse of this whole story, the recoil energy lost is about 0.02 of an electron volt, 2 times 10 to the minus 3 electron volts. That sounds small. It is small in everyday terms, but compare it to the natural line width of that iron 57 transition. The width the line would have in a perfect world with no thermal motion and no external effects. Just the quantum mechanical uncertainty from the excited state's finite lifetime. That natural line width is about 5 times 10 to the minus 9 electron volts, 5 billionths of an electron volt. The recoil energy is about 2/1000ths of an electron volt. The natural line width is about 5 billionths of an electron volt. The recoil energy is larger than the natural line width by a factor of roughly 1,000,000. Let that sit for a moment. The recoil energy is 1,000,000 times larger than the natural line width. This means that the gamma ray emerging from a free iron 57 nucleus is shifted downward in energy from the transition energy by an amount 1,000,000 times greater than the line's own width. The emitted gamma ray is 1,000,000 line widths away from where it needs to be if it is to be absorbed by another iron 57 nucleus. Because the same thing happens in reverse at the absorber. When a free iron 57 nucleus tries to absorb a gamma ray, it will recoil in the other direction, and this time the recoil costs energy from the incoming photon. The absorbing nucleus needs a gamma ray with slightly more energy than the transition energy to compensate for what the recoil will take away. So the emission line is shifted down, and the absorption line is shifted up. And between them there is a gap 1,000,000 times wider than either line. They miss each other completely, perfectly, by a factor of 1,000,000. You cannot have resonant absorption of gamma rays from a free nucleus, because the emitted gamma and the absorbable gamma are tuned to completely different frequencies, displaced from each other by a margin that makes the mismatch between even a badly tuned radio station and the signal it is chasing look like precise alignment. The recoil catastrophe, as it might fairly be called, does not diminish the signal, it abolishes it. And this was the second wall that stood between physicists and any gamma-ray measurement precise enough to detect a gravitational shift. Even if you could make gamma rays, you could not use them for resonance because they recoiled away from resonance on emission and on absorption both. And the two lines were so far apart they would never meet. It seemed definitive, final, not a problem waiting for a clever solution, but a simple law of physics that said no. Until 1958. Until a young man working in a basement laboratory at the Max Planck Institute for Medical Research in Heidelberg, Germany, noticed something that was not supposed to happen. His name was Rudolf Ludwig Mössbauer. He was a doctoral student. He was working with iridium-191, a different nucleus from iron 57, but one that also emitted a gamma ray and was therefore subject to all the same recoil arguments, all the same logic that said resonance should be impossible. He was trying to study the scattering of gamma rays, looking for a particular kind of nuclear resonance fluorescence, not because he expected to find it clean and pure, but because he wanted to understand the way the temperature of his sample affected what he observed. This is a quietly important detail. He was not looking for what he found. He was looking at temperature dependence. He was doing a systematic check, varying the temperature of his iridium sample, expecting to see the expected gradual changes in scattering rate as thermal motion changed and as the Doppler broadening shifted. He expected the measurement to be a tidy confirmation of understood physics. Instead, at lower temperatures, the resonance got stronger. Not weaker. Stronger. This was entirely the wrong result. Cooling a sample of free nuclei should not produce stronger resonance scattering of gamma rays. If anything, cooling reduces thermal motion, which should slightly narrow the Doppler broadened lines, but it should not dramatically change the overall resonance, and it certainly should not make it appear where the recoil argument said it should be absent. Mössbauer was puzzled. He repeated the measurements, he checked for errors, he considered and rejected several explanations, and eventually he arrived at the right one, which was both simple and astonishing. When the iridium nucleus was embedded in a crystal lattice, when it was not floating free in a gas or liquid, but was instead locked into a rigid, crystalline solid bonded to its neighbors. Constrained and held in place, a fraction of the gamma-ray emissions happened without any recoil at all. 0, none, not, approximately none. Exactly none. The nucleus still emitted its gamma-ray, but instead of the recoil energy going into the motion of the individual nucleus, it went nowhere, because the nucleus was not free to move. It was locked into the crystal. And the crystal, as a whole, could potentially recoil. A crystal is not infinitely rigid, but the crystal was so vastly more massive than a single nucleus that the amount of energy it would need to absorb in order to recoil by even the tiniest measurable amount was negligible. The crystal takes the momentum, yes, but taking momentum at negligible cost in energy when your mass is enormous is something very large objects do all the time. When a bullet strikes a wall, the wall takes the momentum, and the energy goes into deforming the bullet and heating the wall, not into sending the wall noticeably flying. In the crystal's case, at low temperatures especially, a fraction of emission events happen with no phonon created at all, no vibration of the lattice, no jiggling of the crystal, which means no energy taken from the gamma ray whatsoever. The recoil was absorbed by the crystal as a whole, spread across its enormous effective mass, and the fraction of energy per nucleus was so small as to be truly negligible. The gamma ray came out with its full energy, unshifted, sharp, not smeared by recoil, not displaced by even a fraction of a line width. What emerged in those recoil-free events was a gamma ray at exactly the transition energy, defined not by thermal motion or recoil displacement, but by the quantum mechanical lifetime of the excited state alone, that natural line width of about 5 billionths of an electron volt. And the absorbing nucleus, equally frozen in its own crystal lattice, would accept the gamma ray without recoiling. So its absorption line was also sitting at exactly the transition energy, undisplaced. They matched. For the first time, you could have resonant nuclear absorption of gamma rays in a crystalline solid. The recoil catastrophe, the wall that the simple physics of momentum conservation had seemed to build permanently into the situation, was circumvented. Not broken, the physics was entirely correct. But the assumption of a free nucleus was wrong. Lock the nucleus into a crystal at low enough temperature, and a significant fraction of emissions and absorptions happen as if the nucleus were infinitely heavy, as if it were nailed to the floor of the universe. Mössbauer published his findings in 1958. He was still a doctoral student. He was working with iridium-191, as we said, but the principle he discovered was general. It applied to other nuclei with the right properties. And among all the nuclei that physicists would go on to study with this new tool, one would rise above all the others as the most useful, the most exquisite, the most breathtakingly sharp instrument that the Mössbauer effect would produce. Iron 57. That 14.4 kiloelectron volt gamma. The same nucleus whose recoil catastrophe we calculated a few minutes ago. Because for iron 57, everything aligned in a particularly fortunate way. The nucleus was abundant enough to work with. The gamma energy was in the right range. The lifetime of the excited iron 57 state was about 141 nanoseconds. Not so short that the line was broad, not so long that the transition was impractically slow. 141 nanoseconds gives you a natural line width via the quantum mechanical uncertainty relation of a few parts in 10 to the 13th relative to the gamma energy. A few parts in 10 trillion. Sharper than almost anything else in physics. And the source was clean. Iron 57 in its excited state is produced by the radioactive decay of cobalt 57. Cobalt 57 decays by electron capture, absorbing one of its own inner electrons, and turns into excited iron 57, which then emits the 14.4 kiloelectron-volt gamma and drops to its ground state. You embed cobalt 57 in an appropriate crystal lattice, and as it decays, it produces a steady stream of these recoil-free gamma rays, each one at the transition energy, each one defined to a precision of a few parts in 10 trillion. A few parts in 10 trillion. Where the gravitational shift over 22.5 meters was 2.5 parts in 1,000 trillion. 2.5 parts in 10 to the 15th, which is still smaller by a factor of roughly 100 than the natural line width of the iron 57 transition. The gravitational shift over 22.5 meters was 100 times smaller than even the sharpest gamma-ray Mössbauer's effect could produce. So the recoil-free gamma from iron 57 in a crystal was sharp enough to serve as a ruler for frequency, vastly sharper than anything anyone had before, but the shift it needed to measure was still smaller than the width of the ruler's markings by a factor of 100. This sounds like we are still stuck. And in one sense, we are. But this is where the way the Mössbauer technique is actually used changes everything. Because you do not detect a gravitational shift the way you might imagine, by looking at the position of the line and seeing that it has moved slightly. You detect it a different way. You use the sharpness of the line not as a ruler you read passively, but as a detector you tune actively. Here is the idea. You have a source and an absorber, both iron 57 in crystal lattices, both tuned to the same razor-thin frequency. In normal conditions, no gravitational difference between them, the source emits a recoil-free gamma at exactly the right energy, the absorber absorbs it, and you detect very few gammas passing through, because most of them are being captured. Maximum absorption. A dip in the transmitted intensity. Now imagine you want to detune them slightly. You want to shift the source's emission frequency by some tiny amount, say, to cancel a gravitational shift you have introduced by putting the source and absorber at different heights. You do not need to build a new source with a slightly different energy. You move the source. Physically, the Doppler effect shifts the frequency of the emitted gamma by a fraction equal to the source's velocity divided by the speed of light, and because the gamma line is so sharp, even a velocity of a few millimeters per second is enough to sweep the emission across the entire resonance and back out the other side. The Doppler tuning range, measured in millimeters per second, covers the whole natural line width. Velocity becomes the energy axis. Mössbauer spectra are literally plotted with velocity on the horizontal axis in millimeters per second rather than in energy or frequency units. It is one of those wonderful moments in physics where a very abstract quantity, frequency, energy at the nucleus scale becomes something you can manipulate with something as ordinary as a motor and a ruler. And this means that any shift in the resonance frequency caused by a chemical environment, by a magnetic field, by a gravitational height difference, shows up as the need to move the source at a corresponding velocity to restore resonance. The gravitational shift does not need to be larger than the line width. You do not need to see the line move by more than its own width. You need to find the velocity that cancels the shift and restores maximum absorption. That velocity tells you precisely and unambiguously the size of the frequency shift. You are using the sharpness of the line not as a measuring stick but as a balance, and you balance it by finding the exact speed of source motion that brings it back into tune. The gravitational shift over 22.5 meters corresponds to a source velocity of about 7 times 10 to the minus 7 meters per second. 7/10 of a micrometer per second. Under a micrometer per second. Less than 1,000th of a millimeter per second. So small that it sits far below the millimeter per second scale at which the gamma line's own width is expressed. But it is exactly the right size to detect, in principle, by finding the precise Doppler cancellation. All of this was, in principle, available by the end of 1958. Mössbauer had published. The community had begun to understand what had been found, and in Cambridge, Massachusetts, in the Jefferson Physical Laboratory at Harvard, two people, one of them a physicist who had already made his mark in a different corner of nuclear physics, and one of them his graduate student, young and precise and patient, were beginning to think about whether the stairwell in their building might be tall enough, and sharp enough, and quiet enough to catch a gamma ray arriving at the top with slightly less energy than it had at the bottom. Whether a prediction that had waited 40 years for a controlled test might finally, in a 65-foot tower in a university building, meet the instrument it had been waiting for. They would have to think about what could go wrong. And there was one thing, in particular, that could go very wrong indeed. Something quiet and almost invisible. Something that had nothing to do with gamma rays or crystal lattices or stairwells. Something as mundane as the temperature of the air in a building on a winter morning that could fake their entire result without announcing itself at all. An enemy subtle enough that they would spend months thinking about how to fight it. But that is where we are going next. And there is no need to rush toward it. You have followed something complicated tonight. Something full of nuclei and line widths and recoil energies and fractions of fractions, and you have done it quietly, lying still, letting it wash through you. You do not need to hold every number. Let them go, if they have already drifted. What is worth keeping, if anything, is the shape of the thing. The shape of a problem so locked, so seemingly final, the recoil catastrophe, a gap of 1,000,000 line widths between emission and absorption, that every physicist who looked at it saw a wall. And then a young man in Heidelberg working on a quite different question, cooling his iridium sample and watching the absorption grow stronger instead of weaker, and puzzling over it long enough and carefully enough to understand that the wall was not a wall at all. It was a door, and the door opened when you locked the nucleus into a crystal so rigid and so cold that the recoil had nowhere to go but into the whole enormous mass of the lattice itself, which accepted it without complaint, taking the momentum but giving back the energy, so the gamma ray came out perfect, unshifted, sharp as the universe would allow. Mössbauer was still a graduate student when he found this. He was in his late 20s. He published in 1958. 3 years later, the Nobel Committee in Stockholm would give him their prize in physics, sharing it with Robert Hofstadter. He was 32 years old. It was one of the faster routes from discovery to Nobel that the 20th century had seen, which tells you something about how clearly the physics community understood, almost immediately, what had been unlocked. What had been unlocked was a tool of almost absurd precision. A gamma ray from cobalt-57 decaying into excited iron-57, the 14.4 kiloelectron-volt transition, the 141 nanosecond lifetime, giving a natural line width sharp to a few parts in 10 trillion, embedded in a crystal so that a fraction of every emission was recoil-free and sat exactly at the transition energy. This was now a tuning fork for frequency itself, more stable and precise than almost anything else a physicist could put on a bench. And as soon as people understood what it was, They began to think about what you could do with it. Some of them thought about chemistry, about the way the electron environment around an iron nucleus in different compounds would slightly shift the transition frequency. The isomer shift, it would be called, giving you a fingerprint of the chemical state of iron in whatever material you were looking at. Some of them thought about magnetism, about the way a strong magnetic field inside a material would split the nuclear energy levels and produce a pattern of gamma absorption lines you could read like a map of the internal field. Some of them thought about crystal symmetry, and how the arrangement of charges around a nucleus would split the levels in a different way, giving you the quadrupole splitting, another fingerprint of local structure. And at least two of them, Robert Pound, who had made his name as one of the co-discoverers of nuclear magnetic resonance, and who knew more than most about the art of precision measurement, and his graduate student Glenn Rebke thought about a stairwell, about a 22.5-meter vertical drop in a building in Cambridge, Massachusetts, about a source at the bottom and an absorber at the top, or the other way around, about a prediction that had been waiting, patient and untested, in any laboratory on Earth since at least 1907, and about what it would take, what it would truly take, in practice, in a real building with real equipment and real air and real temperature gradients, to catch the shift and be sure it was real. Rest for a moment now, there is no rush. The stairwell is there, Pound and Rebke are there. The cobalt-57 is already decaying. Even in this imagined moment, steadily and reliably, each disintegrating nucleus handing off its energy to an iron-57 nucleus that holds it for 141 nanoseconds and then releases it as a gamma ray, recoil-free, sharp as a whisper, into the air of a physics building on a quiet morning in 1959. We will go up the tower together, in just a little while. But for now, if you are warm and still, and the strangeness has settled around you the way a thought sometimes does just before sleep takes it from you, that is exactly right. There is nowhere else you need to be. So let's talk about what actually happens when a nucleus lets go. Not a free nucleus floating in open space, not an atom drifting in a warm gas, jostled by its neighbours, buzzing with thermal motion. Something very different, and in its way something very strange, a nucleus held fast, gripped by a rigid architecture of bonds and forces, embedded so deeply into a crystal lattice that it cannot move on its own even if it wants to. That is the heart of it. That is the trick. And if you have been lying there wondering, somewhere in that comfortable half-aware place between thinking and not thinking, exactly how you make a gamma ray that is sharp enough to act as a ruler for the whole of gravity, this is where the answer lives. Let's go slowly. There's time. Picture an ordinary crystal. Not anything exotic, just a solid material, the kind of orderly arrangement of atoms that makes glass hard, that makes a snowflake, that makes metal ring when you strike it. At the deepest level, a crystal is a lattice, atoms sitting in their prescribed positions, connected to their neighbours by electromagnetic forces that act a little like springs. Each atom has a place, and the energy cost of pulling it away from that place is real and measurable. The whole structure has a stiffness. It resists being deformed. Now imagine one of those atoms contains a nucleus that is about to emit a gamma ray. In an ordinary situation, a nucleus floating free in a gas, say, when that nucleus releases the gamma, something unavoidable happens. The gamma flies away carrying momentum. And momentum is conserved, so the nucleus, which was sitting still, must now be moving in the direction opposite to the gamma, kicked backward like a cannon when it fires a shell. This kick carries energy, kinetic energy. And that kinetic energy has to come from somewhere. It comes from the gamma. The gamma that is released carries slightly less energy than the nuclear transition itself, because a sliver of that energy has been handed to the recoiling nucleus. And when you then want that gamma to be absorbed by another nucleus of the same type, a nucleus that is waiting with exactly the right appetite, tuned precisely to the energy of this transition, you run into a problem. Because the absorbing nucleus also recoils when it accepts the gamma. It kicks backward as the gamma is captured, and so the absorption event also costs a sliver of energy. The result is this: the emission line and the absorption line, which should overlap perfectly, which should be tuned to exactly the same frequency, the same energy, like two radios on the same station, are instead shifted apart. The emitted gamma comes out a little below the transition energy because the nucleus recoiled when it fired. The absorbed gamma needs to arrive a little above the transition energy because the absorbing nucleus also has to recoil. The two lines miss each other. And the question is, by how much? In the case of iron 57, the numbers are almost grotesque in their disproportion. The natural line width of the 14.4 kV gamma from iron 57, the intrinsic sharpness of that transition, determined by the lifetime of the excited state, is roughly 5 billionths of an electron volt. 5 times 10 to the minus 9 in the units physicists use for this. That is an almost indescribably narrow slice of the energy spectrum. It is the sharpness that makes everything possible, as you'll see in a moment. But the recoil energy of a free iron 57 nucleus emitting or absorbing a 14.4 kV gamma is roughly 2/1000ths of an electron volt. 2 times 10 to the minus 3. That is, and it is worth pausing here, because the number is important. That is about 1,000,000 times larger than the line width. 1,000,000 times larger. The two lines, emission and absorption, are separated from each other by a gap that is roughly 1,000,000 times the width of each line. Trying to get them to overlap is not a matter of fine-tuning. It is like trying to thread a needle with a rope. The resonance, the sharp, clean, perfect reabsorption that Mössbauer spectroscopy depends on, simply does not exist for a free nucleus. Or rather, it did not exist, until Mössbauer found a way to make it exist. He was a graduate student at the time. A young German physicist working at the Max Planck Institute for Medical Research in Heidelberg, which has an interesting name for a physics laboratory, but that is another story, and he was working in the late 1950s with a different isotope entirely, iridium-191, rather than iron 57. But the principle he found applies across the whole class. What Mössbauer realized, partly through calculation, partly through careful experiment, was that when the emitting nucleus is not free, when it is instead locked into a rigid crystal lattice, something remarkable becomes possible. The nucleus still wants to recoil. The momentum is still conserved. Nothing about the physics of the emission has changed. But now the nucleus is attached, through its bonds, through the lattice, to an enormous number of other atoms. All of them connected, all of them coupled together by those spring-like forces. The nucleus cannot recoil independently of the rest. When it tries to kick backward, it tries to kick the whole crystal. And the whole crystal is enormous on the scale of a nucleus. Not enormous in human terms. The crystal you might actually use in an experiment might be a few milligrams, a speck you could lose in a fold of paper, but compared to a single nucleus, it is effectively infinite. Its mass, for the purposes of the recoil calculation, is so much larger than the nucleus's mass that the recoil energy becomes negligible. Not just small. Negligible, vanishingly, magnificently small. The whole crystal shifts, if it shifts at all, by a velocity so tiny that the kinetic energy it carries is unmeasurably close to zero. So the gamma ray is released without the recoil penalty. It comes out carrying the full energy of the nuclear transition, not a sliver below, the full amount. Its frequency is not shifted. Its line is not displaced from the absorption line. It is sharp. Sharp as physics allows. Sharp to the level of the natural line width, which is set not by any imperfection in the apparatus, but by the fundamental quantum mechanical lifetime of the excited state. This is the Mössbauer effect. Recoilless nuclear resonance fluorescence. The name is a bit of a mouthful when you say it all at once, but each word is doing real work. Recoilless, the nucleus does not kick. Nuclear resonance, the gamma energy matches the nuclear transition exactly. Fluorescence, the gamma is emitted and can be reabsorbed by another nucleus in the same way. All three words matter. And it matters that this only works sometimes. Not every emission event in a crystal is recoilless. A crystal is not perfectly still. Its atoms vibrate, always, because of thermal energy. The vibrations of a crystal are quantized, and the quanta of vibration are called phonons. When a nucleus emits a gamma, there is a probability that the emission will excite one or more phonons. Will, in effect, dump the recoil energy into the vibrational modes of the lattice. When that happens, the gamma is shifted in the old way, and resonance is lost for that photon. But there is also a probability that the emission will excite no phonons at all. None. The lattice absorbs the recoil without any vibrational excitation whatsoever, and the gamma comes out with its full, sharp, beautiful energy. This probability, the fraction of emissions that are recoil-free, is called the Mössbauer factor, or sometimes the recoil-free fraction, and it behaves in a way that is intuitive once you think about it. It gets larger when the crystal is colder. At lower temperatures, the lattice vibrates less. The atoms are closer to their resting positions. The phonon modes are less likely to be excited by any given emission event. So the fraction of recoilless emissions goes up. This is why early Mössbauer experiments often worked with cooled samples, dipping the crystal in liquid nitrogen or liquid helium to suppress the lattice vibrations and push the recoil-free fraction higher. The stiffness of the lattice also matters. A lattice with a higher Debye temperature, a more rigid crystal with stronger bonds, has a higher recoil-free fraction even at the same temperature. The Debye temperature is a measure of how stiff the spring-like forces between atoms are, how resistant the lattice is to vibration. A hard, stiff crystal clings to its nuclei more tightly, and a more tightly gripped nucleus is more likely to transfer the whole recoil to the crystal as a unit without shaking it. So the recoil-free fraction is a balance. Cold temperatures and stiff lattices push it up. Warm temperatures and soft lattices push it down. It is never 100%, but it can be large enough that a significant fraction of the gamma rays coming from the source are sharp enough to resonate with the absorber. And it was this fraction, this precious minority of perfectly tuned gamma rays that Mössbauer identified, measured, and handed to the world as a new kind of tool. He published in 1958. He was a young man working in Heidelberg, and the paper he published described something that was, at first, somewhat difficult for the community to accept, partly because the effect seemed almost too good to be true. and partly because some of the earliest responses were simply disbelief. If a nucleus in a crystal emits a recoilless gamma, the emission frequency should match the absorption frequency with almost unimaginable precision. But that implied a kind of frequency standard, a kind of ruler, far beyond what anyone had been working with. It was real. Within a year or two, laboratories around the world were confirming the effect, refining it, extending it to other isotopes, and beginning to realize what it meant for everything from fundamental physics to chemistry to materials science. The Nobel Committee did not wait long. In 1961, just 3 years after the publication, Rudolf Ludwig Mössbauer shared the Nobel Prize in Physics. He was 32 years old. The co-recipient that year was Robert Hofstadter, who had done beautiful work on the structure of the atomic nucleus using electron scattering. Both men had, in their different ways, found new windows into the nucleus. But Mössbauer's window was the one that was about to change how a measurement could be made, and to bring a prediction that had been sitting in Einstein's notebooks for half a century down from the cosmic scale to the scale of a building. Now, let's talk about iron 57. Because while Mössbauer made his original discovery with iridium-191, it was iron 57 that became the workhorse of the field. And the reason is a combination of fortunate properties that fall together into something almost preternaturally useful. Iron 57 is not the most common form of iron. The most abundant isotope is iron 56, which makes up more than 90% of natural iron. Iron 57 makes up about 2%. But it has a nuclear excited state with properties that, for precision measurement, are nearly ideal. The transition energy is 14.4 keV. That's kilo-electron volts, the unit of energy used for X-rays and gamma rays. 14.4 thousand electron volts. This puts the gamma ray in a useful range, energetic enough to travel through a reasonable thickness of material, but not so energetic that the recoil problem becomes insurmountable, and not so low in energy that competing effects dominate. The lifetime of that excited state is approximately 141 nanoseconds, 141 billionths of a second. That might sound brief, and it is in human terms, but for a nuclear excited state, it is actually quite long. And here is why that matters. There is a fundamental relationship from quantum mechanics between the lifetime of an excited state and the sharpness of the energy it emits. The relationship is Heisenberg's uncertainty principle applied to time and energy. A long lifetime means a narrowly defined energy. A short lifetime means a poorly defined energy, a broad line. So the 141 nanosecond lifetime of iron 57's excited state translates into a natural line width of about 5 billionths of an electron volt, 5 times 10 to the minus 9 eV. And relative to the transition energy of 14,400 eV, that line width represents a fractional sharpness of about 1 part in 10 to the 13th, 1 part in 10 trillion. Pause with that for a moment. 1 part in 10 trillion. As a fraction of the gamma's energy, the uncertainty in its energy is that small, smaller than anything you could weigh, measure, or build from ordinary materials. The sharpness is not a function of the quality of the equipment. It is written into the quantum mechanics of the nucleus itself, set by the lifetime of the excited state. And nothing can make it worse short of causing the crystal to vibrate. This is what turns a lump of iron 57 into a ruler for frequency. Not a ruler in the mechanical sense, not something you lay alongside a beam of light and read off a number, but a ruler in the sense of a reference standard, a precise known energy against which other energies can be compared. If you have a source of iron 57 gamma rays emitting recoillessly, and you have an absorber of iron 57 tuned to the same transition, then any change in the gamma's energy, however small, will change whether the absorber accepts or rejects it. The absorber is tuned to within 1 part in 10 trillion. If the gamma arrives even slightly off that mark, the resonance falls and the gamma passes through rather than being captured. That is the detector. That is how you measure. Now there is one more thing you need, and it is elegant almost to the point of being funny when you first encounter it. You need a way to tune the gamma's energy across the resonance, to scan it, to find exactly where the absorption peaks and map out its shape. And you do this not with any electronic circuit, not with any exotic field or quantum device. You do it by physically moving the source. You move it toward the absorber or away from it. And by doing so, you Doppler shift the gamma's frequency, just as a moving ambulance siren shifts in pitch as it passes you. But here is the thing about the scale. The natural line width of iron 57's gamma at 1 part in 10 trillion corresponds to an energy so narrow that you can sweep across the entire resonance simply by moving the source at a few millimeters per second. That's it, a few millimeters per second. Walking pace is about 1,000 millimeters per second. A snail moves at roughly 1,000 millimeters per minute, which is roughly 15 millimeters per second. The Doppler velocity needed to move across the entire Mössbauer resonance of iron 57 is slower than a snail. This is why Mössbauer spectra are plotted not against energy in electron volts, but against source velocity in millimeters per second. The velocity is the energy axis. If you push the source away from the absorber at 2 millimeters per second, you are blue shifting the absorber's perspective by a specific tiny amount, moving the resonance to a higher apparent energy. If you pull it toward the absorber at 2 millimeters per second, you are red shifting it. By controlling the velocity precisely, by sweeping it slowly through a range of a few millimeters per second in each direction, you can map out the entire absorption spectrum. And this is not a difficult velocity to control. The mechanical engineering here is straightforward. A motor drive, a loudspeaker coil, a simple oscillation. Nothing exotic. The exotic part is already done. The nucleus did it by sitting still in the crystal. So what does such a spectrum look like? At its simplest, for a bare iron 57 nucleus in a featureless environment, no magnetic field, no electric field gradient, no chemical effects, you would see a single sharp dip in the transmitted gamma intensity, centered at 0 velocity. Source and absorber at rest, they are perfectly resonant. Move the source and the resonance shifts. The dip is narrow, deep and precise. But in practice, iron 57 is almost never in a featureless environment. Iron atoms sit in molecules, in compounds, in metals, in minerals, in proteins. The electrons around the iron nucleus are distributed differently depending on the oxidation state of the iron, the nature of its chemical bonds, the symmetry of its coordination. And these electronic environments push and pull on the nuclear energy levels in ways that shift and split the absorption line. The isomer shift, which you may have heard mentioned in what came before, arises because the electron density at the nucleus is slightly different in different chemical environments, and this changes the nuclear transition energy very slightly. It shows up as a horizontal displacement of the absorption spectrum along the velocity axis. The more electron density at the nucleus, the more the transition energy shifts. And because the isomer shift measures something, The oxidation state of iron, roughly speaking, it becomes a fingerprint. You can look at a compound containing iron, record its Mössbauer spectrum, and read off something about the electronic state of the iron just from where the absorption dip sits on the velocity axis. If the local electric field gradient at the nucleus is not zero, if the environment around the iron atom is not perfectly symmetric, the nuclear excited state splits into two sub-levels, and what was one absorption dip becomes two. This is quadrupole splitting. The size of the splitting tells you about the symmetry of the local environment. Different minerals, different compounds, different geometries around the iron atom produce different characteristic quadrupole splittings. And if there is a magnetic field at the nucleus, either an external field or the internal magnetic field produced by unpaired electrons in a magnetic material, the nuclear levels split further into six, and the spectrum becomes a sextet, six absorption dips arranged symmetrically around zero velocity, spaced in a pattern that encodes the magnitude of the local magnetic field. This is magnetic hyperfine splitting. 3 fingerprints, 3 separate pieces of information, each readable from a Mössbauer spectrum, each telling you something different about the iron atom's local environment. The isomer shift for oxidation state and electron density. The quadrupole splitting for local symmetry. The magnetic hyperfine splitting for magnetic ordering and internal fields. Together they form a fingerprint as unique, in many cases, as the compound itself. Iron oxides have their characteristic spectra. Iron sulfides have theirs. Iron-containing proteins have theirs. Iron minerals of every kind carry their signatures in the pattern of dips along the millimeter per second axis. This is not a side note to the main story of the Pound-Rebka experiment. This is the tool that Pound and Rebka inherited. The new capability that Mössbauer handed to them in 1958, the apparatus, conceptually if not literally the same apparatus, that they realized they could point upward in a stairwell and use to measure a prediction that had been unreachable for half a century. But before we follow them up the stairwell, let's stay for a moment longer with Mössbauer himself, because there is something worth noticing about the speed of what happened. He published in 1958. He received the Nobel in 1961. 3 years. That is not how science usually moves. Normally, the time between a discovery and its Nobel Prize is measured in decades, often 20 or 30 years, sometimes more. The Nobel Committee is not known for haste. But the Mössbauer effect did something unusual. It was verifiable immediately by anyone with the right isotope and a simple mechanical drive. The experiment required no special infrastructure, no enormous particle accelerator, no kilometre-scale interferometer. It required a small crystal, a radioactive source, a detector, and a motor that could be driven at a few millimeters per second. Laboratories around the world confirmed it within months. And the implications for chemistry, for material science, for nuclear physics, and especially for the fundamental physics of relativity were obvious enough that the Nobel Committee moved with unusual speed. Mössbauer was 32 years old when he received the prize. A young man in Heidelberg who had locked a nucleus into a crystal and listened to what it had to say. And what it had to say, among other things, was this: for the first time in the history of physics, you had a source and detector of electromagnetic radiation, gamma radiation, specifically, whose frequencies were matched to within 1 part in 10 trillion. Not approximately. Not within the measurement error of the instrument, within the fundamental quantum mechanical line width of the nuclear transition itself. that had never existed before. Nothing had ever been built or found that could match frequencies to that precision. Not in optics, not in radio, not in any part of the electromagnetic spectrum. The Mössbauer source and absorber pair was the sharpest frequency standard that had ever been made available to physics. And Robert Pound, sitting in Cambridge, Massachusetts, at Harvard University, knew what that meant. He had spent years thinking about precision measurement. He was, after all, one of the men who had helped develop nuclear magnetic resonance, NMR, the technique that could read the local magnetic environment of a nucleus by watching how it precessed in an applied magnetic field, and which would eventually grow into MRI, into the medical imaging that has saved countless lives. He knew precision. He knew what it felt like when a new tool arrived that was better than everything that had come before. And he knew about the gravitational redshift. He knew that Einstein had predicted, from the equivalence principle alone, from the simple, beautiful argument that a freely falling frame of reference is locally indistinguishable from deep space, that a photon climbing out of a gravitational field loses energy. He knew the governing relation delta nu over nu equals g over c squared. He knew that for a height of about 22.5 meters, the height available in the stairwell of the Jefferson Physical Laboratory on the Harvard campus, that ratio came out to about 2.5 times 10 to the minus 15. 2.5 parts in 1,000 trillion. And he now knew that the iron 57 Mössbauer line had a fractional sharpness of roughly 1 part in 10 trillion. The line width was not, by itself, enough to resolve the shift. The shift was a few parts in 10 to the 15th, and the line width was a few parts in 10 to the 13th, meaning the gravitational shift was only about 1/100th of a line width. You could not simply look at where the absorption dip sat and read off the gravity signal. But here is the deeper cleverness, and it is worth staying with it. You didn't need the shift to be bigger than the line width to measure it. You needed something subtler. You needed the ability to detect a small change in how well the source and absorber were in resonance. A small change in the transmitted intensity as the resonance condition shifted slightly due to gravity. And you had a tool for that. You had the moving source. If you placed the source at the bottom of the stairwell and the absorber at the top, the gravitational redshift would cause the gamma rays to arrive at the absorber with slightly less energy than the absorber expected. The absorber, sitting higher in Earth's field, is tuned to a slightly higher energy than a source lower in the field. The gamma arrives a tiny bit below resonance. The transmission is slightly higher than it would be at perfect resonance, because the resonance condition is slightly off. But now you move the source. You push it very gently toward the absorber, upward, in this case, toward the top of the tower, at exactly the right speed to add a Doppler blueshift that compensates for the gravitational redshift. You are using the mechanical motion of the source to cancel, precisely, the energy that gravity has stolen from the gamma ray. When the source moves at exactly the right speed, resonance is restored, the absorption dip returns. And that speed, the cancellation speed, is the measure of the gravitational shift. You have converted an energy difference of 2.5 parts in 10 to the 15th into a velocity measurement. How fast do you have to move the source to compensate for gravity? About 7 times 10 to the minus 7 meters per second. 700 nanometers per second. Less than a micrometer per second. About 3 times slower than the hour hand on a clock moves at its tip. That is the speed at which the source must creep to cancel the gravitational redshift over 22.5 meters. It is one of those numbers that sits at the intersection of the absurdly small and the suddenly measurable. Too small to see, too small to feel, but not too small to control, with the right motor drive and the right careful calibration in a physics laboratory. Pound understood this, and he understood something else. He had a graduate student named Glenn Rebke who was capable and careful and methodical, and he had a building with a stairwell of the right height, and he had the Mössbauer effect, which had arrived from Heidelberg like a gift, and all of it pointed toward the same answer. They could do this. For the first time, they could do this, not up a star, not across a galaxy, not in any cosmic arena that required patience over astronomical timescales, but in a building in Cambridge, Massachusetts, in 1959. And so they began to prepare. The preparation was not simple. Nothing about a measurement at this level of precision is simple, even when the concept is clear. The concept, by now, is almost crystalline in its elegance. Take a Mössbauer source, place it at one end of a 22.5-meter vertical path, place a Mössbauer absorber at the other end, sweep the source velocity while measuring the transmission, and look for the velocity at which resonance is restored as a function of whether the beam is traveling up or down. Subtract the two cases to isolate the gravitational effect. Done, but between the concept and the measurement, there is always a country of complications. And Pound and Rebke were about to enter that country, one careful step at a time. The source was cobalt-57. Not iron-57 directly, cobalt-57 is the precursor. Cobalt-57 is radioactive, and it decays by a process called electron capture. One of the inner electrons of the cobalt atom is absorbed by the nucleus, converting a proton to a neutron and transforming the cobalt-57 nucleus into an excited iron-57 nucleus. That excited iron-57 nucleus then relaxes by emitting the 14.4 keV gamma ray that the whole experiment depends on. So the source is a small amount of cobalt-57 embedded in a suitable host material, a material whose crystal lattice would hold the cobalt atom, and then the daughter iron atom firmly enough to produce recoilless gamma emission. The details of the host material matter because the Lamb-Mössbauer factor depends on how tightly the lattice grips the nucleus, and you want it as high as possible. The absorber was iron-57. A thin foil or coating of material enriched in iron-57, positioned at the other end of the beam path. The enrichment matters because natural iron is mostly iron-56, which doesn't participate in the resonance at all. To get a strong absorption signal, you want the iron-57 fraction to be higher than the natural 2%. The detector was a photon counter positioned on the far side of the absorber, measuring the gamma rays that got through. When resonance was strong, more gammas were absorbed and fewer got through. When resonance was weak, more gammas passed through. The variation in transmitted count rate as the source was swept in velocity was the signal. And the source had to move. Smoothly, controllably, reproducibly, they used a combination of mechanisms, a slow, steady drive to set the mean velocity, and a loudspeaker-type transducer for fine control. The velocity had to be known to within a fraction of the measurement window, which, given that the window was something like a millimeter per second across, meant the velocity control had to be precise at the level of a fraction of a millimeter per second, reproducibly over many hours of data taking. This was not easy, but it was achievable. The mechanics of it were within the range of what a careful physicist with good machining support could build. What was harder, subtler, more dangerous was something else entirely. temperature, the temperature of the source and the temperature of the absorber. You might not expect temperature to be the nemesis of this experiment. But there is a second-order effect, a relativistic effect actually, one that comes from special relativity rather than general relativity, that couples the thermal motion of atoms in a solid to the frequency of the gamma rays they emit. Even in a rigid crystal, even at low temperatures, the atoms are not perfectly still. They vibrate. And because they vibrate, they are moving, on average, relative to the observer. Moving atoms, even in random thermal motion, even when the average velocity is zero, have a mean squared velocity that is not zero. And a source whose atoms are in thermal motion emits gamma rays that are shifted in frequency by an amount proportional to the mean squared velocity. This is the second-order Doppler shift, also called the transverse Doppler shift, and it depends on temperature. The key fact is this: if the source and the absorber are at exactly the same temperature, their second-order Doppler shifts are the same, and the effect cancels out. But if there is a temperature difference between them, even a very small one, the gamma rays from the source arrive at the absorber with a frequency offset that is proportional to the temperature difference. How large is this offset? For iron 57, a temperature difference of roughly 1 degree Celsius between source and absorber produces a fractional frequency shift of approximately 2.4 times 10 to the minus 15 per degree, 2.4 parts in 1,000 trillion per degree. And the gravitational shift they were trying to measure was 2.5 parts in 1,000 trillion. 1 degree. One single degree of temperature difference between the cobalt 57 source at the bottom of the stairwell and the iron 57 absorber at the top could produce a spurious shift comparable to the entire gravitational signal they were hunting. This was not a small systematic error to be corrected with a factor of 2. This was a potential disaster. The temperature gradient could fake the whole experiment. It could produce a measurement that looked exactly like the gravitational redshift, or that cancelled it, without gravity playing any role at all. Pound and Rebke knew this, and they thought carefully about what to do. The solution was not to eliminate the temperature difference, though they controlled temperatures as carefully as they could. The deeper solution was in the experimental design itself. They ran the beam in both directions. First, the source at the bottom and the absorber at the top, with gamma rays travelling upward. Then, they reversed it, source at the top, absorber at the bottom, with gamma rays travelling downward. The gravitational effect reverses sign when you reverse the direction. A gamma ray climbing up loses energy, arrives at the top slightly redshifted, slightly below resonance. A gamma ray falling down gains energy, arrives at the bottom slightly blue-shifted, slightly above resonance. The shift is the same size in both cases but opposite in sign. Gravity is antisymmetric in direction. The temperature systematic, by contrast, does not reverse cleanly with direction. If the bottom is warmer than the top by some amount, it is warmer regardless of which end you put the source on. The spurious shift from the temperature difference has the same sign in both runs, so if you subtract the upgoing measurement from the downgoing measurement, or equivalently, add them with appropriate signs. The temperature systematic tends to cancel while the gravitational signal adds. It is not perfect. Nothing is perfect, but it gives you a powerful handle on the dominant systematic error. This is the elegance of experimental design at its best. Not the elimination of error, but the arrangement of the measurement so that error and signal behave differently under a simple manipulation and can be separated. They were almost ready. The stairwell was there, the cobalt-57 was decaying, the iron-57 absorber was waiting at the top of the tower. 1959. Jefferson Physical Laboratory, Harvard University. A quiet building. A vertical shaft of about 22.5 meters, a source that would need to creep at under a micrometer per second to compensate for what gravity does to a climbing photon. And downstairs, two physicists who had thought very carefully about what it would mean to be sure. Somewhere in this, if you are still following, there is something that might feel like a held breath. As if the whole long chain of reasoning, Einstein's equivalence principle, the failure of ordinary spectroscopy, Mössbauer's quiet discovery in Heidelberg, the mathematics of the recoil-free fraction, the 3-year sprint to a Nobel, the cobalt-57 source and its iron daughter, the millimeter-per-second velocity axis, the sub-micrometer compensation speed, the temperature demon waiting inside the stairwell's air, all of it is pointing toward one moment, one measurement, one number that will either match what Einstein wrote down in 1907 or will not. And before we go up the tower with them, it is worth noticing something about where we are in this story. We are in a building. An ordinary building on an American university campus. The stairwell is not in outer space. The gamma source is not mounted on a rocket or a satellite. The absorber is not on a different planet. The distance involved is 22.5 meters, the height of a moderately tall house, the span of about 8 floors in an old building. The distance you might walk in 10 or 12 seconds, and in this building, at this height, between two physicists who had thought hard about temperature gradients and direction reversal and source velocities, measured in fractions of a millimeter per second. In this building, the prediction that Einstein had written down before the full theory of general relativity even existed was about to be tested and confirmed. For the first time anywhere on Earth that was not the surface of a star or the disk of the sun. That is where we are. The tower is waiting. Pound and Rebka are there. And if you have drifted a little, somewhere in the long satisfying chain of nucleus in crystal and recoil, free fraction and temperature demon, if the numbers have blurred gently into the warmth of wherever you are. That is perfectly fine. The measurement will still be there when you need it. The gamma rays are still climbing. The shift is still 2.5 parts in 1,000 trillion, patient and small, and exactly as real as Einstein said. And we will go up together in just a moment. So, let's go up. The first thing to understand about what Pound and Rebka actually did. The physical. Step by step. What they built with their hands version of it is that the experiment had two distinct problems to solve simultaneously, and neither one could be solved without the other. The first problem was the shift itself. They needed to measure a fractional change in frequency of about 2.5 parts in 1,000 trillion. That is, as we have established, an almost violently small number. And the way they were going to read it was by using the Mössbauer effect as a kind of tunable resonance detector. The iron-57 absorber at the top of the tower would drink in the gamma ray with maximum efficiency only when the ray arrived at exactly the right energy, the natural line-width energy of the 14.4 keV transition, and would reject it, would let it pass through. The instant the energy drifted even slightly off. But the gravitational shift, that draining of energy over 22.5 meters, was so small that it moved the gamma's frequency by only a whisker-thin sliver of that already impossibly narrow line width. To see it, they needed to know, very precisely what the resonance absorption looked like as a function of energy. They needed to walk the energy up and down across the resonance and map the shape of the curve. And the way to walk the energy of a Mössbauer gamma up and down is to move the source. Physically move it. Because of the Doppler effect, the same shift in frequency you hear when a car passes you on a road, the sound rising as it approaches and falling as it recedes. Moving the source toward the absorber presses the gamma's frequency upward, and moving it away tugs the frequency down. The relationship is clean and exact. And because the line width of the iron 57 gamma is so breathtakingly narrow, it takes only a very small source velocity, a few millimeters per second, to sweep the gamma's energy all the way across the resonance from one side to the other. This is the thing that should make you stop for a moment and sit with it. A few millimeters per second. That is slower than a careful snail. It is slower than a minute hand on a large clock. It is roughly the speed at which your fingernails grow. And moving the source at that pace was enough to shift the gamma's frequency by the entire width of the resonance, because the resonance itself was so impossibly sharp. Now, the gravitational shift they were looking for, the energy the gamma lost climbing 22.5 meters against Earth's pull, corresponded to a source speed of about 7/10 of a meter per second. Let me say that differently. 700 nanometers per second. Less than a micrometer per second. About 1,000th the thickness of a human hair, covered in a single second. That is the velocity at which the source would need to move toward the absorber to exactly cancel the gravitational energy loss, to restore the gamma to its original frequency after the climb had drained it. At that speed, the Doppler gain would precisely replace what gravity had taken. So the second problem, and it is almost more daunting than the first, was this: how do you move something at under a micrometer per second, steadily, controllably, and know that you are doing it? What Pound and Rebke built was a combination of two motion systems. One was a slow hydraulic drive, a mechanical system that could push the source at a very gently controlled creep. The other was something closer to a loudspeaker, a transducer driven by an oscillating electrical signal that could add a known, controllable velocity to the source in a sinusoidal cycle, moving it toward and away from the absorber rhythmically. By adjusting that oscillating velocity, they could apply a known Doppler shift that could be tuned to precisely offset or augment the gravitational effect. The resonance absorption at the far end of the tower would tell them, by its strength, how close they were to the right compensation. Think of it like tuning a radio in the dark. You can't see the dial, but you can hear the static clearing when you're getting close and the music sharpening when you've found the station. Pound and Rebke were tuning a gamma ray to an absorber separated by a flight of stairs, using a source mounted on a loudspeaker drive, listening for the resonance to sharpen. And they ran it both ways, up and down. This is the part of the experiment that shows the most care, the most real, practiced thoughtfulness about what could go wrong. They sent the beam from the basement to the roof of the stairwell, cobalt 57 source at the bottom, iron 57 absorber and detector at the top, gamma rays climbing 22.5 meters against gravity. And then they swapped the geometry. Source at the top, absorber at the bottom, gamma rays falling 22.5 meters with gravity. Why does this matter? Because gravity is not the only thing that can shift a gamma ray's energy. There are other effects, temperature differences between the two ends of the tower, mechanical vibrations in the building, tiny variations in the source or the absorber themselves, and many of these spurious shifts would be roughly the same in both directions. They would shift the apparent resonance frequency up by a constant amount, regardless of whether the beam was going up or going down. But gravity's shift reverses sign when you reverse direction. A gamma climbing upward loses energy, arrives drained, appears to have shifted toward lower frequency. A gamma falling downward gains energy, arrives enriched, shifted toward higher frequency. The gravitational effect is antisymmetric. It changes sign with the beam direction. The spurious systematic effects, in many cases, do not. So by running both directions and subtracting, by taking the difference between the upward result and the downward result, Pound and Rebke could isolate exactly the part that reversed sign, which is exactly the gravitational contribution, and wash away the symmetric contamination that stayed the same in both runs. It is a beautiful piece of experimental logic. Simple, once you see it. The kind of thing that makes you think, of course, that is how you do it, and then you remember that they had to think of it first. But there was still the temperature demon. And the temperature demon very nearly had them. We mentioned it before, a little while ago, in the quiet warning that there was an enemy lurking. Now let us meet it properly. When an atom or a nucleus is warm, it is moving, jittering in place, vibrating, oscillating with the thermal energy of its environment. And because it is moving, randomly, in all directions, the gamma rays it emits are slightly Doppler shifted, some toward higher frequency, some toward lower. For an ensemble of warm atoms, this broadens the emission line. But there is also a subtler effect, the second-order Doppler shift, sometimes called the relativistic or transverse Doppler shift, and it matters here in a way that is not immediately obvious. For a source that is warm, that is, for atoms moving at a temperature-dependent average speed, there is a net shift in the emitted frequency that depends on the mean square speed of the atoms, which depends on the temperature. The hotter the source, the faster the atoms are moving on average, and the more this second-order effect shifts the gamma's central frequency downward. It is not a broadening. It is an actual shift of the line itself in a direction that can mimic or mask the gravitational shift. And the size of this thermal shift, for realistic laboratory temperatures, is comparable to the gravitational shift from 22.5 meters. Comparable, a source that is 1 degree Celsius warmer than its absorber can produce a second-order Doppler shift of roughly the same magnitude as the entire effect they were trying to measure. 1 degree. Not a dramatic, easily avoided temperature excursion. 1 degree. The difference between standing near a window and standing away from it. The difference between a lamp on one side of the stairwell and no lamp. The difference between morning and afternoon. If the cobalt-57 source in the basement was 1 degree warmer than the iron-57 absorber at the top of the tower, the thermal shift it introduced would contaminate the gravitational signal at full strength, and they might not know. They might measure a beautiful number, agree with Einstein to 10%, and never realize they were looking at a thermal artifact wearing general relativity's clothing. So Pound and Rebke monitored the temperatures. They monitored them obsessively, continuously, carefully. They knew the temperatures of both ends of the tower, and they accounted for the thermal contribution to the frequency shift in their final analysis. They did not assume the temperatures were equal. They measured them, and they corrected for the difference. This is, and it deserves to be said plainly, the unglamorous heart of real experimental physics. Not the elegant idea, though the idea was elegant. Not the Nobel-winning mechanism, though the mechanism was extraordinary. The heart of it was two physicists in a stairwell worrying about temperature gradients and writing down numbers on clipboards, and when they had collected their data, run the beam upward and downward, tracked the thermal corrections, mapped the resonance absorption curves with their Doppler tuning source, and done their subtractions, the answer came out at about 10% of the prediction. 10% agreement in 1959. The measured gravitational shift matched the Einstein formula /= g/c², with h of 22.5 meters, giving 2.5 parts in 1,000 trillion, to within about 10%. Now, 10% might sound like a generous margin, and if we were talking about measuring the length of a room, it would be catastrophically poor. But in the context of what they were doing, the first controlled laboratory confirmation of gravitational redshift, measuring a shift of 2.5 parts in 1,000 trillion over a distance a person could walk in about 10 seconds, 10% agreement, was a triumph. It meant the measurement was real. It meant they had found the effect. It meant Einstein's 1907 prediction, derived from an equivalence argument alone, without the full machinery of general relativity, was not an abstraction or a philosophical curiosity. It was a measured fact, confirmed between two floors of a Harvard building. And they were not finished. 5 years later, in 1964, Pound returned to the problem, this time with a different collaborator, a physicist named Joseph L. Snyder. They had spent those 5 years understanding the systematic errors more deeply, refining the temperature measurements, improving the apparatus. And in 1964, the Pound-Snyder experiment produced a result that agreed with Einstein's prediction to about 1%. 1%. Not 10. 1. The same stairwell. The same 22.5 meters. The same iron 57. The same 14.4 kV gamma, the same recoilless trick discovered by Rudolf Mössbauer in a laboratory in Heidelberg 6 years earlier. But now the measurement was tight enough, clean enough, controlled enough to say, we are within 1% of the number Einstein wrote down when the century was still new, when relativity was still being assembled, when quantum mechanics was only a word in a handful of letters between anxious men in universities across Europe. 1% agreement. In a stairwell. And here is the beautiful thing, the thing worth sitting with before we let the story unfold into the wider world where it went next. Pound and Rebka were not confirming relativity as an astronomy result. The way the bending of starlight around the sun was confirmed during the 1919 eclipse. They were not confirming it as a cosmic observation, the way the redshift of distant galaxies is confirmed with telescopes pointed at the edge of the observable universe. They were confirming it as an engineering result, a measurement made with a loudspeaker drive and a hydraulic transducer and temperature probes on a stairwell wall in the Jefferson Physical Laboratory at Harvard University in the middle of an ordinary Tuesday, or whenever it was, in 1959. It was a basement experiment. Almost literally. The source was in the basement. The detector was in the upper floor of the building, and it confirmed one of the stranger things a human being has written down, that gravity reaches into light itself and quietly takes a little of its energy away, leaving it slightly poorer after a climb, slightly richer after a fall, exactly as if the photon, the particle of no rest mass, the thing that has no weight in the classical sense, were carrying a burden proportional to its energy, and paying a toll measured in the formula E over c² times g times h. The photon climbs. It pays. The meter is Einstein's equation. and Pound and Rebke read the meter. Now, if it had stayed a Stairwell result, if it had been filed away as an elegant confirmation of a corner of general relativity and never gone anywhere, it would still be one of the finest experiments of the 20th century. But it did not stay in the Stairwell. The physics travelled, and one of the places it travelled was approximately 20,000 kilometres overhead. There are about 30 active satellites in the global positioning system at any given time, orbiting the Earth at an altitude of around 20,200 kilometres. Each one carries an extremely precise atomic clock. And the whole system depends, fundamentally, on time. It works by measuring how long a signal takes to travel from the satellite to the receiver in your pocket or your car or your phone. Time multiplied by the speed of light gives distance, and triangulating distances from several satellites at once gives your position. The precision of your position is directly proportional to the precision of the timing. Nanoseconds matter. Fractions of nanoseconds matter. And at 20,000 kilometers above the Earth's surface, time runs differently than it does at sea level. Not by much, not by anything a person would notice with a watch, but by enough to matter to a navigation system. There are two effects. They pull in opposite directions. The first is the gravitational one. The same Einstein shift that Pound and Rebke measured in a Stairwell, now operating over 20,000 kilometers rather than 22 meters. At that altitude, Earth's gravitational field is weaker than at the surface. A clock at altitude, sitting higher in the gravitational well, runs fast compared to a clock on the ground. It gains time. The fractional difference in gravitational potential between the satellite's orbit and the Earth's surface means the satellite clocks tick forward at a rate that accumulates, if uncorrected, to about 45 microseconds per day. Fast, running ahead. The second effect is special relativity, not general relativity. The satellites are moving. They orbit at roughly 14,000 kilometers per hour, and a moving clock runs slow compared to a stationary one, a consequence of special relativity that is entirely separate from gravity. The satellite's orbital speed causes its clocks to lose about 7 microseconds per day compared to clocks on the ground. Slow, falling behind. The two effects don't cancel. They add in different directions, plus 45 microseconds per day from gravity, minus 7 microseconds per day from orbital speed. The net result is that satellite clocks run fast by roughly 38 microseconds per day compared to clocks on the ground. They gain time. Every day, without correction, a GP's satellite clock would drift ahead of the ground-based clocks that the system depends on by 38 microseconds. 38 microseconds. That sounds negligibly small. Let's see what 38 microseconds of timing error does to a GPS position. Light travels at 300 million meters per second. In 38 microseconds, 38 millionths of a second, light travels about 11 kilometers. So a GPS system that ignored the relativistic clock drift would accumulate a position error of roughly 10 to 11 kilometers per day. Every day, growing. After a week of ignored relativistic effects, the GPS in your phone would tell you that you are somewhere between 10 and 70 kilometers from your actual location. You would drive into the wrong city. You would land an aircraft in the wrong country. You would be somewhere that the map says is a field when you are in fact standing on a motorway. This is corrected. It is engineered out. The satellite clocks are deliberately set to run slow by exactly the amount needed to compensate, Before they are even launched, the frequency of their oscillators is adjusted downward by a calculated fraction to offset the relativistic gain they will experience in orbit. The adjustment is based on the same physics that Pound and Rebka measured in their Stairwell, the same g/c squared, the same equivalence principle that Einstein wrote down in 1907. Every time you look at a map on your phone and it shows you accurately where you are, every time the blue dot is in the right place, a relativistic correction is running quietly inside that answer. The one Robert Pound and Glenn Rebka measured in a 22.5-meter tower in 1959 is not a different correction. It is the same one, operating at greater altitude, doing the same arithmetic that the Stairwell first verified. The tower was 22 meters, the satellite is 20,000 kilometers up. The physics is identical. We should sit with that for a moment. The blue dot on your map. The turn-by-turn direction that tells you to bear right in 400 meters. The quiet confidence with which a navigation system knows where you are to within a few meters. All of it depends on a correction that was first measured in a Stairwell. All of it traces back to a graduate student in Heidelberg who noticed, in 1958, that a nucleus locked into a crystal could spit out a gamma ray without kicking back. And back further still, to Einstein writing down the equivalence principle in 1907, before he had the full theory, before he had the field equations, before he had general relativity in the form the world came to know it, writing it down because the logic of falling elevators and bending light demanded it. The Stairwell at Harvard was not the end of the story. It was the confirmation that the story was true. And the story kept going. In 1976, a hydrogen maser, a different kind of atomic clock, one based on hydrogen atoms rather than iron gamma rays, was loaded into a Scout rocket and launched to an altitude of about 10,000 kilometers. This was the Gravity Probe A experiment. At that altitude, the gravitational time dilation was measurable with the maser's extraordinary precision, and the result agreed with the prediction of general relativity to within about 70 parts per million. 70 parts per million. That is a tenfold improvement over even the careful Pound-Snyder result from 1964. The same effect confirmed again at higher altitude with greater precision. But Gravity Probe A stayed close to Earth. It went up and came down. It confirmed the number to a new decimal place and was celebrated among physicists, and then, as experiments do, it was filed away. What happened next was different. What happened next involved a journey of 200 million kilometers, give or take, and a pair of robots sitting on the surface of another planet. The Mössbauer effect from the beginning was a laboratory technique. You could use it to fingerprint materials, to read the internal magnetic fields in a piece of iron, to identify the oxidation state of an atom by the tiny energy shift caused by the electrons around it, to map the crystal symmetry of a compound by the splitting of its resonance line. The three signatures that Mössbauer spectroscopy reads, the isomer shift, the quadrupole splitting, the magnetic hyperfine splitting, each encodes something different about the atomic and electronic environment of the iron nucleus, and together they form a fingerprint as individual as a handprint. Different iron compounds have different Mössbauer spectra, and with practice you can identify a mineral from its spectrum the way you might identify a piece of music from its first few notes. This is a powerful thing to be able to do with iron. Iron is one of the most common elements in the universe. It is the endpoint of stellar nucleosynthesis in ordinary stars. Iron is where stars run out of nuclear energy to release, the ash of stellar burning, and so it accumulates in rocky planets, in asteroids, in the surfaces of worlds. Mars is red because its surface is rich in iron oxide. The redness of Mars, visible to any ancient human being who looked up at the right time of year and saw the wandering reddish star, that redness is iron. A Mössbauer spectrometer on the surface of Mars would be able to tell you, from the fingerprint of the gamma absorption, exactly which iron minerals were present. Not just iron in general. Specific minerals, with specific histories, with specific conditions required for their formation. This is what NASA decided to include on the Mars exploration rovers. Spirit and Opportunity, both launched in 2003, both landing on Mars in early January 2004, each carried a miniaturized Mössbauer spectrometer called MIMOS 2. The instruments used a cobalt-57 source, exactly as Pound and Rebka had used, to illuminate the Martian surface with 14.4 keV gamma rays and read the absorption spectrum from the iron-bearing minerals in the rocks and soil. The cobalt-57 in those instruments, on Mars in those robots, was decaying by electron capture into excited iron-57, exactly as Rudolf Mössbauer's laboratory samples had done in Heidelberg in 1958. The gamma ray that emerged, recoilless, sharp, defined at the natural line width of the iron-57 transition, was reading the surface of another planet. Think about what that is. A technique born from a graduate student's observation that a nucleus in a crystal doesn't kick back when it emits, turned into a frequency ruler by the recognition that a ruler that fine could detect a gravitational shift over 22 meters, carried across 200 million kilometers of space on a robot the size of a golf cart, reading iron minerals on the surface of Mars. What Opportunity found at Meridiani Planum, the broad, flat plain near the Martian equator where it landed, included two iron minerals whose presence together said something remarkable. One was hematite, iron oxide. Specifically, it was present in small rounded spheres scattered across the surface like tiny ball bearings, nicknamed blueberries by the science team because of their color in certain imaging modes. Hematite can form without water in certain volcanic or hydrothermal conditions. But the other mineral Opportunity's Mössbauer spectrometer found was jarosite, and jarosite is different. Jarosite is a sulfate mineral. It contains iron and sulfate and potassium or sodium or other ions, and it forms only in the presence of water, specifically in the presence of acidic water, water that is chemically active and mineral-rich. Jarosite does not form in dry conditions. It does not form in simple volcanic environments. On Earth, it forms in acid mine drainage and in places where sulfide minerals have been weathered by acidic liquid water. Finding jarosite on Mars was not a hint. It was not a suggestion. It was a mineral that could only be present if liquid water, acidic, active, real water, had once been there, on that plane, on that world. The hematite blueberries, meanwhile, were small enough and rounded enough to have formed in water too, concretions precipitated from mineral-rich solutions percolating through sedimentary rock, the way similar formations appear on Earth. Taken together, the Mössbauer signatures pointed at a Mars that had not always been the cold, dry desert it is today. A Mars that had once, in some chapter of its past, been wet. And the instrument that read those signatures, the instrument that delivered from the surface of another planet. One of the clearest pieces of evidence that Mars once had liquid water was a Mössbauer spectrometer. Its cobalt-57 source, its iron-57 gamma, the same 14.4 keV transition, the same recoilless emission, the same impossibly narrow line that had let Pound and Rebka see a shift of 2.5 parts in 1,000 trillion in a Harvard stairwell. A basement experiment. A Mars discovery. The same nucleus. It is difficult to know where to put that thought. It doesn't fit comfortably into any single category. Not pure physics, not astronomy, not geology, not the history of technology. It is all of them at once, threaded together by a single experimental fact discovered by a 24-year-old in Heidelberg who noticed that the numbers didn't make sense unless the whole crystal was taking the recoil. And now it is late, wherever you are. Or early. Or somewhere between the two, the hour that belongs neither to day nor to night, when the thoughts come more slowly and the world outside has gone quiet. Let us come back to the stairwell one more time. It is 1959. The Jefferson Physical Laboratory at Harvard University. Robert Pound has spent years thinking about nuclear magnetic resonance. He is, in fact, already known partly for his work on NMR, the technique that eventually became the basis of MRI scanners in hospitals. And he has turned his attention, with Glenn Rebka, to this new thing that Rudolf Mössbauer found, this recoilless gamma, this impossibly sharp energy. And they have built something in the stairwell, a source on one end, an absorber on the other. A Doppler drive moving the source at speeds that are measured in micrometers per second and millimeters per second, velocity as the energy axis, the resonance as the listener at the far end of the tube. The shift they are looking for is 2.5 parts in 1,000 trillion. The gravitational toll that Earth's field levies on every photon that climbs away from it, over every meter of height. Their 22.5 meters give them a number so small that just slightly more than 1 degree Celsius of temperature difference between top and bottom could manufacture the same shift from scratch, out of thermal physics, with no gravity involved at all. They know about the temperature demon. They watch it. They correct for it. They run the beam up and down and subtract. They are careful in the way that good experimenters are careful, not worried, not anxious, but precise and methodical, the way a craftsperson is precise, knowing that the care is not separate from the work, but is the work itself. And the answer, when it comes, is there. The resonance shifts. The shift reverses when they reverse the beam. The subtraction isolates the anti-symmetric part. The thermal correction accounts for the systematic. And what is left, after all of that, is a measured fractional shift of 2.5 parts in 1,000 trillion, or thereabouts, in a direction consistent with Einstein's equation, at a magnitude consistent with Einstein's equation. From a measurement made in a building that anyone with a university library card could have walked into. 10% agreement in 1959. 1% by 1964, and the prediction had been written down in 1907. Before quantum mechanics was complete, before the full field equations of general relativity, before the transistor, before the computer, before anyone had imagined that one day small robots carrying the descendants of this technique would land on Mars and read the mineral memory of an ancient, wet, acid-rich ocean that no human eye had ever seen. The prediction was written in 1907. The confirmation came in 1959. And the confirmation came not across a galaxy, not from the light of a distant quasar, not from a neutron star or a white dwarf or any of the cosmic, unreachable, spectacular objects we tend to associate with general relativity. It came from a stairwell, 22 meters tall. In Cambridge, Massachusetts, there is something in that which stays with you. Or it stays with me at least, and I hope it stays a little with you too, wherever you are, however close to sleep. We live with gravity so constantly, so casually, that we have stopped noticing it. It is the thing that makes things fall. It is the weight of your body against the surface you're lying on right now, wherever that is. A bed, a couch, a chair. Gravity is the pressure of the mattress, the pull at the back of your eyelids, the feeling of settling. We know it only as a mechanical thing, a thing that makes apples fall and planets orbit. But Einstein said it was something else too. He said it reached into the fabric of light and time themselves. He said a beam of light climbing away from the Earth was not simply passing through gravity, it was paying it, handing over a small, exact portion of its energy. Calculated by a formula so simple you could write it on a napkin, arriving at the top of its climb, slightly drained of colour, shifted toward the red, measurably, provably older. He said this in 1907. He derived it from a thought experiment about falling elevators and the impossibility of distinguishing acceleration from gravity. He wrote it in a paper. And then, for 50 years, almost nobody could confirm it on the scale of a room or a building or anything a person could touch. The only evidence was stars and sunlight, and those were dirty, contaminated by gas motions and pressure shifts, and in the case of the famous Sirius B measurement by Walter Adams in 1925, by scattered light from the companion star that couldn't be properly disentangled from what was being measured. And then a graduate student in Heidelberg noticed that a crystal could take the recoil, that a nucleus locked in a rigid lattice could emit a gamma ray into the world without kicking, so the gamma emerged with an energy as sharp and clean as physics allows. And that observation, not a grand theory, not a famous name, not a Nobel prediction, just a careful observation in a laboratory that turned out to have a surprising result, gave two physicists in Massachusetts the tool they needed to climb the stairs. You are of this. Not metaphorically, not poetically, or not only poetically. The atoms in your body are iron-containing. Hemoglobin carries iron. In your blood, right now, the same iron that Pound and Rebke used as their absorber, the same iron that Mimos II interrogated on the surface of Mars. Your body is iron and water and carbon and the same elements that the Mössbauer spectrometer is designed to read. You sit in a gravitational field that is right now, at this moment, doing to the light around you what Einstein predicted it would do, bending the frequency of every photon climbing upward from the floor to your ceiling. By 5 parts in 1,000 trillion, for every 22 meters, patiently and exactly, whether or not anyone is watching. The GPS satellite passing overhead right now, and there is almost certainly one overhead, one of 30-odd satellites in their 20,000-kilometer orbits, is running its clocks at a rate adjusted by exactly the amount general relativity demands. 38 microseconds per day, carried forward as a correction into every position fix. And when you next look at a map on a screen and trust the blue dot to tell you where you are, you will be trusting, at one remove, the Pound-Rebke measurement. You will be trusting the Mössbauer effect. You will be trusting Einstein's 1907 thought experiment about what a person in a falling elevator cannot tell about the world outside. None of that requires a black hole. None of it requires a pulsar, a neutron star, a gravitational wave, a cosmic-scale catastrophe. It requires a building in Cambridge, Massachusetts, a 22.5-meter stairwell, a loudspeaker drive, a cobalt-57 source, and 2 physicists who were careful enough about temperature gradients and direction reversal to see in the data the minuscule signature of something real. That is what science looks like from the inside, sometimes, not the dramatic announcement, not the sweeping telescope image, the temperature probe, the direction reversal, the subtraction, the check and the recheck. The quiet notebook entry that says, "The shift is there. The numbers agree. Within 10%. Within 1%. The thing Einstein wrote in 1907 is real." We started this journey in that stairwell a long time ago in the narration, or perhaps just a little while ago if you have been drifting in and out, which is perfectly fine. The gamma rays were climbing. The shift was 2. 5 parts in 1,000 trillion. Pound and Rebka were there. And now you know how they did it. Not just that they did it, but how. The nucleus in the crystal, the recoil taken by the whole lattice, the iron 57 line so sharp that velocity in millimeters per second sweeps across its entire width, the Doppler drive moving the source slower than your hair grows, the up and down runs, and the subtraction that separated gravity's signature from every other contamination. The temperature demon tamed by patience and measurement and careful accounting. You know about the GP's satellites carrying that correction silently in their clocks, keeping your blue dot honest by a grace of 38 microseconds per day. You know about the small robot on the floor of Meridiani Planum, reading jarosite and hematite in the Martian dust, the same cobalt 57 source, the same iron 57 gamma, the same impossibly sharp line, now pointing at a world 200 million kilometers away and saying, water was here. Acidic water. Real water. In some chapter of this planet's long past, something was wet. And you know that all of it, the GP's fix and the Martian mineral and the temperature corrected Harvard Stairwell result traces back to the same chain. Einstein in 1907. Mössbauer in 1958 in Heidelberg, noticing the crystal. Pound and Rebka in 1959, climbing the stairs. The gamma clock in a basement weighed a falling photon. And the universe turned out to be exactly as strange as the equations said it was. Not more, not less. Exactly. If you have stayed with me this far, if you are still awake, your lamp still on, wherever you are in the world tonight, then thank you. It has been a long and quiet journey, and I am genuinely glad you came. And if you drifted somewhere in the middle, in the beautiful long middle where the nucleus locked into its crystal and the temperature demon crept through the stairwell, and you are only half awake now, catching the last few words, that is lovely too. The stairwell was always here. The gamma rays are patient. The shift is still 2.5 parts in 1,000 trillion. It will keep until morning. If tonight's journey gave you something to carry into sleep, a gentle like and a subscribe means more than you might imagine. Small creators like me rely on your support to keep these slow journeys going. And I would love to know in the comments where you are listening from tonight and what time it is in your corner of the world. There is something I find quietly wonderful about the idea of people in different time zones, different beds, different hemispheres, all drifting off to the same 22. 5-meter stairwell, the same iron nucleus, the same measurement of something so small it took 50 years to pin down. Until next time, settle in. Let the numbers go soft. Let the stairwell recede. Sleep well, fellow voyager. The next journey keeps until you wake.